All right, in this video I want to look at some figurate numbers, some sequences, and talk about some ways to find formulas for them. So we're looking at, it's particular, three types of figurate numbers: the triangular numbers, the square numbers, the oblong numbers. I'm giving some examples like the third triangular number I'm calling T3, or the second square number S2, or the third oblong number O3. And in general, we have these sequences here. But what I want to do is come up with a formula to say, how do I find T sub n, the nth triangular number, or the S sub n, the nth square number, or O sub n, the nth oblong number? Or maybe in more particular terms, if you wanted to know what is like the 100th triangular number, or the 50th square number, or the 94th oblong number, if you had a particular n in mind. You may already know some formulas, I'm guessing you do, to find some of these things. So I want to frame this in looking at two different types of formulas. One kind of formula is a recursive formula, and a recursive formula is one that uses a previous term or terms to get a value. So for example, we might use t sub n minus 1. We might use the term right before t sub n to find t sub n. In more specific terms, maybe if I know t5, how can I get t6? That's the sort of question that a recursive formula would help you with. Another kind of formula is called an explicit formula, and the explicit formulas use the index of the term to get a particular value. The index is that subscript right there. So in general, if you're looking for T100, you might not want to first find T99 and using a recursive formula, because then you would need to find T98 and all the way back to something that you did know. Instead, if you wanted to know a shortcut where you could just take 100 and use that to get the 100th triangular number, for example, that's what we would use an explicit formula for. So I've got some sequences of the first few of these figurate numbers, and I want to start with triangular numbers. And these triangular numbers, I literally copied and pasted these things. So I've got like this whole page of the first 5 triangular numbers over and over and over. And what I really love about this, if you can love mathematics, is I like the way that we can see these numbers grow in different ways. So really, I'd like to say, pause the video and think about, how do you see this pattern growing? Okay, if you've unpaused the video, or if you just went right through that, one way that you could see this pattern growing is we could look and see if we could find the previous triangle, like can you find T2 hiding in T3? Or can you find T3 hiding in T4? And there's lots of different ways. Maybe you see T3 hiding in here, and in the same way you see T2 hiding in T3. And maybe you even see T1, the first triangular number is a dot. That's not really a triangle, or is it? Okay, but I see that hiding in T2, and the same way I see that hiding there. That's not the only way to see those, but that's a way that I've indicated there. You might also have seen these triangles hiding. Maybe you saw T2 hiding in the top and T3 hiding in the top. Or maybe you saw T2 hiding in the bottom corner. So maybe you see them this way. In any of these ways, we get these nice relationships where we have the previous triangular number and then some extra dots. And so using this one as an example, I'm going to say, okay, it looks like T3 is T2, the previous triangle, plus 3 dots, 1, 2, 3 right there. And T4 looks like it's T3 plus 4 dots. And T5 looks like it's T4 plus 5 dots. In working backwards, T2 looks like T1 plus 2 dots. Is there some kind of, in general, formula we can find for T sub n here? I'm thinking T sub n would say, find the one before it, and then add some dots. How many dots? Well, when I was looking at T3, we added 3 dots. T4, we added 4 dots. T5, we added 5 dots. So I'm saying that T sub n is T sub n minus 1, the one before it, plus 5 more dots. This is an example of a recursive formula. And with a recursive formula, not only do I have to say, well, use the previous one and then add, whoops, I said 5, yikes. Add n dots, that's much better. Okay, I feel much better about that. T sub n minus 1 plus n dots, that way it matches up with T sub 3 is T sub 2, then n minus 1, plus 3 plus n plus the index. I also, with a recursive formula, need to say where I'm starting at. So I'm going to start with the first triangular number being 1. And then I can use 1 plus 2 to get 3, and 3 plus 3 to get 6, and 6 plus 4 to get 10, and 10 plus 5 to get 15. There's another formula, another way to look at these numbers, and that way might be looking at this in terms of what these numbers are adding, or how we're combining numbers here. So if I look at this, I might see 1 plus 2, or 1 plus 2 plus 3, or 1 plus 2 plus 3 plus 4. Let me draw some lines to kind of separate how I'm seeing these. Or 1 plus 2 plus 3 plus 4 plus 5. I'm choosing these vertically, but we could also do this in a number of different ways. Maybe we could see this as going 1 plus 2, 1 plus 2 plus 3 diagonal. Maybe you like that. Or we could go horizontal. 1 plus 2, 1 plus 2 plus 3, 1, 2, 3, 4. So we can get this relationship here. A general formula for this, for the nth one, well, this was T2, T3, T4, or T5. T1 is just 1. That pattern actually works. They start with 1 and we stop counting at 1. So T sub n could be thought of as 1 plus 2 plus 3. Keep adding up those natural numbers until you get to the index, the number that you're looking for. This is something that doesn't require the previous number. If you wanted T95, you would just add up 1 plus 2 plus 3 plus 4 all the way up to plus 93 plus 94 plus 95. That would be a long way to do it, but this is an example of an explicit formula. It's probably not my favorite explicit formula because for large indexes, for like T200 or T5000, that would be a T5000. I would have to add up 5,000 numbers. That would be a long way of doing that. But that is an example of an explicit formula. Okay, I want to look at a different kind of numbers, but I'm going to come back to these triangular numbers in just a bit. Next, I want to look at the square numbers. And to kind of mirror the pattern, first I want to see, is there a recursive pattern? Do I see, like, for example, S2 hiding in S3, or S3 hiding in S4? And one place I see S3 is in this corner. Whoops, yikes. I don't like that. Ooh, okay, start over. S3 is hiding in S4. S2, there we go, is hiding in S3. S4 is hiding in S5. And there's really lots of different places you might see it hiding. S1, this 1, I thought that 1 was a triangle. Well, guess what? It's also a square, is hiding right there. And so we can get these squares in here. So S2 looks like S1 plus 3 more dots. Or S3 here is S2 plus 5 more dots. And S4 is S3 plus 1, 2, 3, 4, 5, 6, 7 more dots. S5 is S4 plus 1, 2, 3, 4, 5, 6, 7, 8, 9 dots. So it looks like this is a recursive formula where the first thing is 1, S1 is 1, and Sn is Sn minus 1, the square before it, plus something. Now what is that something? Well, I noticed that these somethings are all odd. 3, 5, 7, 9. Those are odd numbers. I'm guessing the next one would be, for S6, would be S5 plus 11. And S5 is 25. 25 plus 11 is 36. And that is the sixth square number, so that's correct. A way to write odd numbers is 2n minus 1, 2 times n minus 1. Now, can we really see that in the picture? Well, when n was 3, can you see two groups of 3 minus 1? Well, here's a group of 3, and there's a group of 3, but I double counted that corner one, so I need to subtract 1 to undo the double counting. In S4, here's a group of 4, and there's a group of 4, so I'll do 4 plus 4, that's 8, but then I need to subtract 1, so that's where I get that. So that's a recursive formula, thinking about the odd numbers that I'm adding on. Another way to mirror the way I looked at the triangular numbers is to think about this as 1, and for S1, S2 is 1 plus 3, S3 is 1 plus 3 plus 5. So if I make these L shapes, or 7 shapes, these right angles, 1 plus 3 plus 5 plus 7, and S5 will be 1 plus 3 plus 5 plus 7, and then the outer band is 9. This is an example of an explicit formula, but one that would be a little harder to work with. This explicit formula, Sn, would be adding up these numbers. This is not all of the natural numbers, but it is the odd numbers starting at 1. So I think for like S6, I would do 1 plus 3 plus 5 plus 7 plus 9 plus 11. So I want to add up the first 6 odd numbers. How far do we need to go? Well, we need to go to the nth odd number, which happens to be 2n minus 1, the same thing we had up there. So that's an explicit formula, but not my favorite explicit formula. My favorite explicit formula for the square numbers is using the area model for multiplication. And this square is a special kind of rectangle. The area of a rectangle is length times width. And so I could think of this as a 2 by 2 array, and S2 is 2 times 2, or 2 squared. S3, I could think of that as a 3 by 3 array, so 3 times 3, or 3 squared. S5 would be a 5 by 5 array, or 5 squared. And this is a formula I'm guessing that you already knew. Sn is n times n, or Sn, if you like exponents, is n squared. That's actually why we call that second power squared, because it would make a square array. Is this a recursive formula or an explicit formula? Well, I mean, really, it's taking that index and then we're multiplying that index by itself. So we're not using a previous thing. So this is an example of an explicit formula. Okay, let's look at oblong numbers. I'm really excited about these. And then we'll come back to triangular numbers and see some other nicer formulas. So with the oblong numbers, these are rectangles that are kind of built specially so that they're one more unit long than they are tall. That's what an oblong number is. It's not just anything, but the oblong is one more unit long than it is tall. And so, first of all, I'm going to play the find the previous oblong number in the next one. So I'm trying to set myself up with a recursive formula where O2 is O1 plus 4, 1, 2, 3, 4 dots. O3 is O2 plus 1, 2, 3, 4, 5, 6. O4 is O3 plus 1, 2, 3, 4, 5, 6, 7, 8. And can you see the pattern? O5 is O4 plus, I'm guessing it's going to be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. My guess was right. These are adding up. These are taking the previous term and then adding an even number. So for my recursive formula, I'll say O sub n is the previous one plus an even number. So an even number, a way to write that is 2 times n, like 2 times 5 is 10, or 2 times 3 is 6. Can you see the 2 times 5? There's a 5, and there's a 5. There's a 4, and there's a 4 in O4. This is why I really like the figurate numbers, because I can see where the formula comes from and then write it in an algebraic way. With the recursive formula, we also need to say where we're starting at, and the first oblong number is 2. Let's take a look at the formula where I'm looking at adding up a group of numbers. So O1 is just 2. O2 is 2 plus 4, 2 plus 4. O3 is 2 plus 4 plus 6. O4 is 2 plus 4 plus 6 plus 8. Are you seeing the pattern? O5 is going to be 2 plus 4 plus 6 plus 8 plus 10, the first 5 even numbers. And my explicit formula for this would say O sub n is going to be add up the first n even numbers. So start with 2 and 4 and 6 and keep on adding until you get to the nth even number, which is 2 times that index. Another way of looking at these, like I said, the oblong numbers were a rectangle that was one more unit long than it was tall. And so we could look at O1 and say it's 1 times 2. Or O2, that's that rectangle right there. O2 is going to be 2 times 3. And O3 is 3 times 4. And O4 is 4 times 5. And O5 is 5 times 6. So this explicit formula is O sub n is n, the index, times 1 more than the index. O3 was 3 times 1 more than 3. O4 was 4 times 1 more than 4. So that's another explicit formula. Okay, here's where stuff gets really cool. So you might look at that n times n plus 1 and say, you know what, I want to simplify that, or I want to multiply that out and get O sub n is n squared plus n, if we use the distributive property and multiply that n through the parentheses, through that sum. This is another explicit formula, but the cool thing is, can you see this in the diagram? Can you see O4 as 4 squared plus 4, for example? Now, 4 squared, that makes me think of this explicit formula for the squares. Can you see 4 squared? Can you see this 4th square number? Right there. plus these 4 more. And O5 is the 5th square number plus 5 more. So that's really cool. It works all the way down. 3 squared plus 3, 2 squared plus 2, even 1 squared plus 1. So that's super cool. These are 2 different formulas for the oblong numbers, 2 different explicit formulas. I want to show you another one. I want to look at a relationship between the oblong numbers and the triangular numbers. And so here's my oblong numbers again. And now I'm playing the can you find the hidden shapes? But now I'm wondering, can you see 2 triangles? Can you see triangles hiding in here? There's 2 of the triangular numbers. O2 looks like it's 2 times T2. Here's 2 of the triangular numbers there. O3 is 2 times T3. And O4 is 2 times T4. And this isn't really a recursive formula or an explicit formula. This is just a formula that's showing a relationship between oblong numbers and triangular numbers. Specifically, it's showing me that O sub n is 2 times T sub n. This is really cool because this is going to help me get a formula for my triangular numbers. When I left these, I really only had a recursive formula and an explicit formula. And if I wanted to find, say, the 100th triangular number, both of these formulas are going to take me a long time. So if I look at this formula, 2 times the triangular number, I can use the the explicit formula for O sub n, and I can say, my favorite one maybe n times n plus 1 is 2 times T sub n. And I can solve this algebraically for T sub n by dividing by 2. And getting T sub n is n times n plus 1 divided by 2. Let me go ahead and write that down. N times n plus 1, the oblong number for n, and divide it by 2. This is an explicit formula. And now I'm going to say, can we find that hiding in here? So it's half of something, so I feel like I need to draw the other half that used to be there. And T2 is half of O2, which would be 1/2 of 2 times 2 plus 1. Or T3 is half of the 3rd oblong number. Or T4 is half of the 4th oblong number. So we can see that in these pictures. Something else that's cool. Oh, so this is my favorite explicit formula. Now if I want to find T100, I can take 100 times 100 plus 1 and divide it by 2. And that is a lot easier to figure out than adding up all the natural numbers from 1 to 100, or figuring out what the 99th is and the 98th and the 97th, working my way back. So this is my favorite formula for the triangular number. One other thing that I like to look for, I like to find in these square numbers, is I like to play, can I see, I know I already saw square numbers hiding in oblong numbers. Now I want to look and see if I can find triangular numbers hiding in the square numbers. So if I look here, I have a triangular number. There's a triangular number, and up there's another triangular number, but they're not the same. S3 is T3, the 3rd triangular number, plus T2, the 2nd triangular number. S4 is T4, the 4th triangular number, plus the 3rd triangular number. And S5 is the 5th triangular number plus the fourth triangular number. And back here, S2 is T2 plus T1. That's the first triangular number right there. This is a relationship. It's not really a recursive formula or an explicit formula, but it says S sub n is T sub n plus T sub n minus 1. So that's a really cool relationship that we can see there, and that's how we can use some formulas then to figure this out. So that's what I wanted to show you with these formulas and figurate numbers.